Here we can start. I download the link. Thank you. Then, uh, yes, yes, yes. Sorry. Yeah. Okay, so I'm start with Moya and Hirotani. You speak about the basic one speed of engine using Q-freeze. Please. Okay. Thank you for introduction. I'm Tome Hirotani from Kyushu University in Japan. Today, I'd like to begin the presentation titled Relativistic Quantum of the Engine using Q-Trade. What I'm about to talk about is based on the recent paper we uploaded to archive. Oh, sorry, disconnect. Yeah, my laser pointer is disconnected now. Okay. Quantum heat engine I'm going to talk about today is very interesting because properties that that do not appear in the classics appears, and specifically by utilizing the quantum coherence or quantum entanglement as a resource, it can show behaviors that are impossible in the classical system, such as exceeding kernel efficiency. This is classical limit, or or extracting work from a single heat path, and so on. In this study, we are focused on positive work condition, or PWC for short. And in many previous studies, quantum auto engine using a qubit as a working fluid. However, studies using a multi-level system using a qubit are still quite limited. In addition, recent work extends the quantum auto engine into the context of RQI, leading to the development of relativistic quantum auto engine. Here, by relativistic, I mean our heat engine, in which a qubit follows any trajectory, including the stationary or acceleration in a curved spacetime, and interacting with the quantum field as serving as a thermal heat path. However, relativistic quantum auto engine using Q-Tree has not been studied until now, so our study fills this gap. By the way, how exactly is work defined in the context of quantum thermodynamics? In the framework of quantum thermodynamics, let's take a look at how the first law of thermodynamics, including the definitions of work and heat, is formulated based on Aritsky's paper. If the working fluid is quantum system, the general quantum system is represented by the density operator rho, and if the Hamiltonian of the system is H, the internal energy is described in this way. And differentiating this, we can divide it into terms of Rho's derivative and Hamiltonian derivative. Comparing this equation with the first law of dynamics, we can regard this term as corresponding to heat and this term corresponding to work. The reason why we can say this is as follows. First, regarding the heat term, change in the density operator corresponds to the change in entropy. Also, heat flow changes entropy. Thus, they correspond. And on the other hand, the Hamiltonian is a term that we can control. So, for example, when considering the spin system as a working fluid, the energy gap can be controlled by an external magnetic field. Thus, we can manipulate the gap in the same way, much like moving a piston. Also, the work in the classical sense can be written in terms of integral PdV, while the change in Hamiltonian can be written in terms of energy gap. So this is analogy, but we can see that the, the change in volume corresponds to the change in the gap in the classical heat engine. With these definitions of work and heat, let's move on to the main part. We will look at the structure of quantum Otto engine. For simplicity, we will consider the qubit. First is quantum adiabatic compression process. In this process, because it is adiabatic, the qubit is disconnected from the quantum field, while the and the energy gap expands from omega to omega prime, while the state rho remains constant. And next is quantum hot isotope process. In this process, the state changes from rho to rho prime by interacting with the quantum field, while the energy gap, omega prime, remains the same. Next step is quantum adiabatic expansion. The energy, the state rho prime remains constant, but the energy gap is restored to its original width. Finally, we do a quantum cold isosphere to return the state rho prime to its original state rho. And this is one cycle. So let's find the condition called PWC under which work can be extracted in this cycle using a Q-treat. So the Hamiltonian in shading a picture is set up in this way as the Hamiltonian of Q-treat, quantum field, and interaction. Each Hamiltonian is like this. We will start with the Q-treat Hamiltonian. The energy gap is shown on the right figure, labeled omega 01, between level Z and E1, and labeled omega 12 between the level E1 and E2, and Hamiltonian is like this. The quantum field is such a Hamiltonian as the quantum scalar field. This is the interaction Hamiltonian. Through the interaction, the Q-treat transitions to another level. And we will introduce the spin-one operator as the Q-treat transition. What kind of transitions does this operator represent? It represents the transition such as Z to E1 and E1 to E2, where adjacent levels can go. But the transition, such as Z to E2, is not allowed to jump from one level to another. Finally, lambda and chi are the strength and the time of the interaction. Set the initial state of the system. First, the initial state of the Q-trait can be described in this way by using occupancy probabilities P0, P1, and P2 for each level. And the initial state of the quantum field can be any quasi-free state, i.e., a state where the one-point correlation function vanishes when the expected value of the field is taken. Before presenting our result, please let me introduce the feasible C established in previous study. In the case of qubit, the feasible C take this form, and here T effective means effective temperature defined using a response function as shown below. And in the Q-trait case, one might expect that the PwC would take a similarly simple form like this, but the actual behavior is a bit more interesting. So if we write the PwC as an equation, it looks like this. And delta omega represents the difference in the gap changed by the adiabatic process. But since it's hard to interpret directly, so let's take a look at graph instead with S omega 01 on the vertical axis and S omega 21 on the horizontal axis. And the green area indicates where the positive work can be extracted. And I'll now explain how to interpret this graph. First, when the S omega 01 is positive, that is in this region, the following inequality holds as shown here. And conversely, the if it's negative, the direction of the inequality is reversed. Of course, similarly, for S omega 21, S omega 21, when it's positive, uh, that is this region, we have this inequality, and of course, when it's negative, the inequality flips. And combining these two pictures, we obtain the green region on the right. And since the slope is taken to is always taken to be positive, this region corresponds to the cases where the work can always be extracted. What's particularly interesting are these two additional regions where one of the inequality derived from the qubit type feasible C is reversed. And these these regions suggest that it is possible with a Q-trait even in setup where it would be impossible with a qubit. Okay. There are other interesting results as well, but today I presented just these highlights. If you are interested, please refer to our paper for more detail. Thank you for listening. Uh, the the first question is in general. I see. So you mean what happened if we consider the more general transition? I mean, okay. Actually, I calculate the case, but result is so complicated. I mean, we cannot obtain such a simple PWC. I don't know why, but in general, actually, I'm not sure. But today, I present uh, these results as, for the simplicity. And what is the second question? I see. Yeah, I'm sorry. I'm not sure actually. Sorry. I see. I see. Uh, you mean the question is speed of the iceberg process? Yes. Yeah. In this study, we consider the mm, infinite time to uh, to cancel the of diagonal elements, but today I cannot explain what is the of diagonal element, so please refer to our paper. Sorry. Oh, thank you. From the you can use this mic here. That works better for speaking.
This is the laser pointer. Sorry. Okay. Okay, thank you. Hello, everyone. My name is Ireneo. I'm a student of Professor Eduardo Martin Martinez and Professor Adrian Lapascu at the University of Waterloo. I'd like to acknowledge one of our collaborators, Adam Teshido Banfi. I'd also like to thank the organizers of the conference here for allowing me to present my research today. So today I'm going to tell you about non-perturbative methods of entanglement harvesting. It's an ongoing study. And first, I will outline the motivation of our study. Then I will describe both perturbative and non-perturbative methods of entanglement harvesting. Finally, I'll conclude with some of our results. A key prediction of quantum field theory is the existence of correlations between different space-time regions of a quantum field. It is hypothesized that we can measure this phenomenon using the entanglement harvesting protocol, where entanglement between detectors is induced due to their interaction with a quantum field in its vacuum state. However, this protocol has never been tested experimentally. There are some experimental proposals for realizing this protocol using superconducting circuits. How this works is we use a transmission line or a superconducting waveguide acting as our quantum field, and we probe the field using superconducting qubits. Was demonstrated in the lab the ability for ultra-strong coupling between a superconducting flux qubit and a transmission line. The device achieving this is shown, this is an electron microscope image of the device. This ultra-strong coupling regime lies outside the validity of perturbation theory. Moreover, the experiments cited in the previous slide utilize this ultra-strong coupling. So the goal of our study is to develop tools to model entanglement harvesting in the regimes of these experiments, including strong coupling, finite time, and the field confined to a finite region. We'd also like to compare this with the perturbative model. Let's consider two stationary and point-like harmonic oscillator detectors interacting with a 1+1 dimensional quantum scalar field confined to a cavity. I've included the free and interaction parts of the Hamiltonian here. Omega represents the energy gap of a detector. Lambda is the coupling constant. Chi is a switching function controlling whether the interaction is on or off. And we have our field operator here defined in terms of mode functions, which depend on the boundary conditions chosen. We're going to assume identical coupling constants and switching functions between the detectors in each of the field modes. We're also going to assume that the detectors initially start in their ground states and the field starts in its vacuum state at a time t equals 0. To quantify entanglement, we look at the negativity, which for a two-mode system is both necessary and sufficient for the presence of entanglement. To model our system using methods of perturbation theory, we evolve the system using the time evolution operator. Expanding the time evolution operator in a Dyson series, we can acquire the state of the detector system at a time t greater than 0 to leading order in the perturbation. It takes the form of this matrix, and our elements L and M are the contributors to entanglement, which are defined as integrals of a Whiteman function. Negativity can then be calculated using this expression given here. To model our system non-perturbatively, we first choose a cutoff mode and define quadrature operators Q and P. It's easy to show that this Hamiltonian is quadratic in these quadrature operators. Given an initially Gaussian state, this means that our system remains in a Gaussian state for all subsequent times. And so the state of the system can be completely characterized using the vector of means and the covariance matrix. Our initial condition corresponds to a covariance matrix equal to the identity at the initial time, and also a vector of means equal to 0 at all times. Then at subsequent times, we can calculate the covariance matrix as a symplectic transformation, S0 times Si. S0 is generated by the free part of the Hamiltonian, and Si, being the solution to a well-posed initial value problem, is generated by the interaction part of the Hamiltonian. We can then calculate the negativity as a function of the covariance matrix of our detector system. So let's apply both of these methods to identical detectors, a massless field with periodic boundary conditions, and sharp switching. In the space-time diagram given here, we have detector 1 and detector 2. The gray bars indicate when the switching is turned on, and this dashed line indicates the light cone detector 1. I'd like to note that the detectors come into causal contact at T over L equals 1/2. So for a small value of the coupling, we see very good agreement between both the perturbative and the non-perturbative methods. In fact, during space-like separation of the detectors, we see that the detectors can genuinely harvest entanglement from the field. To confirm the validity of our non-perturbative method, we can look at two convergence tests. The first convergence test being plotting the error in the covariance matrix as a function of the step size of the method. And we see that our method converges to high order. We can also look at the error in the covariance matrix as a function of our cutoff mode. And we see that the error monotonically decreases to 0, confirming the validity of our solution. One can then ask what happens when the coupling is increased. It turns out that as we increase the coupling constant, we find a range of values that exhibit behavior seen on the right figure. So for space-like separation, perturbation theory remains a good approximation. However, during light contact and after, perturbation theory begins to break down. Increasing the value of the coupling constant further, we get wild oscillations of the negativity until eventually, as lambda approaches omega, the negativity diverges because the Hamiltonian is no longer semi-positive definite. It turns out that this range of values for lambda depends on the energy gap chosen. To illustrate this, we have two different values of the energy gap. We see this breakdown of perturbation theory in the smaller energy gap case. In the larger energy gap case, we still see good agreement between perturbation theory and the non-perturbative method for all times. So in summary, we applied both an efficient and robust non-perturbative method to model finite time entanglement harvesting for two harmonic oscillator detectors coupled to a 1+1 dimensional quantum scalar field in a cavity. We found that there exists a range of coupling constant values for where perturbation theory is still a good approximation during space-like separation, but begins to break down during light contact. We found that this range depends on the choice of the energy gap, and we also found that perturbation theory fails as lambda approaches omega. As I mentioned, the beginning of this study is still ongoing, and we're currently looking into other experimental regimes, such as continuous switching, coupling to the field derivative, and also the transients of finite time entanglement. Thank you for listening to my talk, and I'm happy to take any questions. Yes, so in those plots, we considered, I think, 200 motes. And it is cut off here, but it does eventually go to 0. So we can see that the covariance matrix isn't changing for 201, 202, and so on. Three levels? No. So in a paper done by, let's see. Yes, in this paper with Rick, Jose, Bruno, and Eduardo, all of the elements of the reduced density matrix of the detectors outside of this basis are zero to leading order. So this matrix is defined in this basis. Sorry, what's the shortest wavelength? So yes, the width of the light cone is half of the length of the cavity. Sorry, I can't really hear your question. Yeah, sorry. Okay, sure. Yeah, sorry. Sorry, the mic keeps cutting out. Yes, say again?
Maybe I'm guessing the orders, but you saw that after causing contact, only one of the regimes work,
Mhm.
the other one doesn't work. Why that is?
We're still exploring why. It could be due to boundary effects or maybe resonance. Not entirely sure yet. So, okay.
Yes, you have to like that to take that transformation is to part.
We don't have to. There is a way to do it using the full F, so as a sum of the free and interaction parts. But it turns out that this method is more stable. Okay.
So the next speaker, long motion. It's fine. I guess.
First, I'd like to thank the organizers for having arranged this really enjoyable conference so far. It's nice to be in a very cool room, so I hope the audience won't be too hot during this talk. So I'd like to speak about this work that I did in collaboration with Leo Parry, Rick Persch, and Jorma Loco. So this was work that we finished around 2 years ago, but then we realized that no one had spoken about it yet. So I'm going to speak about ambient temperature versus ambient acceleration, and we'll get into what ambient acceleration really is in the circular motion Unruh effect. So here's the journal reference, and here's a QR code to the paper itself. So really, this talk is in two parts. First, about the Unruh effect, in which there is this concrete equivalence between acceleration and temperature. And then I want to discuss how far we can push that, how far this duality between acceleration and temperature really holds. So the Unruh effect is the equivalence between the experience of an accelerated observer through the Minkowski vacuum and a static observer in a thermal bath. So this equivalence holds when we say that the proper acceleration of the accelerated observer is let's say A, and then the temperature of the ambient thermal state of this static observer is A over 2 pi. So this is a prediction from 1976. It's well established. But we wanted to see how far this can go. But to push it, we have to understand how we got there in the first place. So within RQI, we have our toolbox of usually the Unruh DeWitt detector model. For the linear acceleration under effect, there are several methods that we could use. We could use a detector model. We could also go geometrically. You could do a Hawking temperature type calculation and arrive at this Unruh temperature. But this operational model that models an observer really experiencing these effects is the model that is most extendable. So the constituent parts are, we have this x. This is some trajectory, usually qualified as stationary, which just has some geometric meaning, and this will just be labeled x. And then we have this detector. Now, we've already seen a few detector models this week, and I'll just use the standard two-level system. There's a ground and excited state, and that will be mu in this interaction Hamiltonian. This will represent our detector, and then we have some phi. This phi is the field, and it's evaluated along this trajectory. So it's just localized along our interaction. Given then this interaction Hamiltonian, we can go through the usual time-dependent perturbation theory and take some limits, and we can arrive at this transition rate f, which just says how often is this detector exciting, if at all. And it's just the Fourier transform of the two-point function in some state. And in this talk, it will either be the vacuum state or a thermal state. Even further in our toolbox, we have a thermometer. In the first talk, we saw an effective temperature, and this is exactly what is shown here again. In the case of uniform linear acceleration, we have that this really is a thermometer, and all thermometers would agree with temperature A over 2 pi. But if we allow some generality, where the state is not strictly thermal, then we arrive at an effective temperature in exactly the same way as Jorma Loco spoke about on Tuesday. So how robust is the Unruh effect? So on one side, we have that the Unruh effect temperature holds in any dimension. So 2 plus 1, 3 plus 1, fractional dimensions. You could consider compactified sections of your space-time, and all your detector would see is exactly the same temperature. But the question that we wanted to investigate is linear acceleration equivalent to a thermal bath in general? What happens if we consider doing something else on top of this linear acceleration? So conceptually, we wanted to add, let's say, circular motion on top of this. So on the left, you have linear acceleration plus circular motion. And on the right, we have a thermal bath plus circular motion. And this is the idea behind the calculation. So geometrically, the way one constructs this is if you consider coordinates, let's say, t, x, y, z, where z is pointing up to the ceiling here. So if you accelerate in z and have circular motion in x and y, these are completely disjoint motions. We can add them together and nothing really changes. It's still quite perfect circular motion if you project onto this plane, and it's still linear acceleration if you project into the tz plane. On the right, we considered a thermal bath with an observer in circular motion. Now, a thermal bath has a preferred rest frame, so you can just choose that the time evolution of the circular motion is the same as the time evolution used to construct the thermal state, and then this is again a stationary situation. So both of these, we can use our response functions, this Fourier transform of the two-point function. So then, with this idea set, you have to ask the question that you want to answer. So lexically, what we wanted to address was, does an observer in circular motion through a thermal bath of temperature A over 2 pi, so where the temperature is fixed at an equivalent Unruh temperature, does it respond in the same way as an observer undergoing uniform acceleration in the z-axis, as well as circular motion in the plane orthogonal? So finally, in this setup, how do you do it? Well, you have to write down two world lines. So on the left in blue, and blue will always respond to our accelerations, we have in the t and z, we have a cinch and a cosh corresponding to this acceleration, and in the middle we have circular motion. And on the right, we also have circular motion evolving in time. Then when you go through, you can write down your response functions, and they're quite complicated objects in this case. But the issue is that they're very different. And so you could just say, we're done. These are distinct phenomena. No, they are not the same in general. If you set r equals 0, so if you squash your circular motion down to the origin, you turn off the circular motion, then these integrals are identical and you recover the Membrere effect again. So in general, no, but that doesn't mean there aren't limiting cases in which we might see that these have similarities, that there's still a robustness persisting. One of these cases is, as I said, if you squash down this circular motion onto a small enough orbit, it's basically just linear acceleration or static motion in a thermal bath. So at this origin, you get the Membrere effect. So one thing you could do is you could expand these integrals in small r, and then look at the difference, and then see how much they're changing. So these integrals you cannot express in closed forms in terms of known elementary functions, but it turns out the difference of them you can, and it's quite a simple function. It all depends on this g, which is x cof pi x, which is quite thermal. When you're doing thermal expectation values, you often get a cof both in classical and quantum field theories. So what do? Of course, you plot it. So on the on your left, we have sections through this heat map on the right. And what happens is we have a maximum, and then it goes down something that looks linearly, and then suddenly 0. And this is much more dramatic here. So purple is the region in which this difference, delta F, is 0. This is a region of pure indistinguishability between the two scenarios. And in fact, this looks very much like lines between them. And so it's almost as if there's complete disjoint areas and regions of parameter space in which these are indistinguishable versus distinguishable phenomena. And this turns out is when the energy gap of the detector is greater than the angular frequency of the circular motion. And so this phenomenon also persists in 2+1 dimensions. So if you do this in 2+1, if you look at circular motion through a thermal bath, this is indistinguishable from inertial motion through a thermal bath in exactly the same region. So if you look at circular motion, if you probe it with too high energies, you start to lose information about the circularity of the motion. So a second region we looked at was what happens if we go in very small energy gaps, and you can expand in powers of E, let's say. You can write down two formulae. So in blue, we have for this accelerated case, and in red for this ambient thermal bath. And in fact, this thermal bath temperature, 2 pi gamma 0, is exactly the same temperature as we saw in the talk on Wednesday in the parallel session on the circular motion effect in annular Josephson junctions. So both are entirely characterized by a single constant, which is just an integral involving the parameters of the motion. But because they're both characterized purely by these single constants, we can look at their difference, and you divide by one of them, so it's dimensionless quantity. So this white region we have when this ratio is greater than 1, and then the rest is somewhere between 0 and 1. So I want to draw attention to two regions of this parameter space, two purple regions. So on this left-hand side, this corresponds to very small a, so very low temperature and very low accelerations. And this is basically when you switch off your thermal bath, you stop the person accelerating, and what do both cases reduce to? They reduce to the circular motion Membrere effect. So you would expect them to agree. And very interestingly, they only agree in a very small region of very small values of a. However, along the bottom, this is the region when r omega. This is turning off the circular motion. So this is the orbital speed of the circularity. When you slowly switch this off, you have quite a large region of purple, much larger than on the other side. And so as you're slowly turning off this circular motion, you expect to recover the Umbra effect. So you get a linear acceleration and you get a static thermal bath. But if you're orbiting slowly enough, even up to, say, 0.1%, 10% of the speed of light, still rather indistinguishable. So this is interesting that this region is much larger than one would a priori expect. But beyond these, yes, you can still tell. So in regions when you have a geometric expectation that they are similar, they're indeed similar. And so the final limit was just a double limit with a slightly surprising result. So if you look at large energy gaps and slow circular motions, you can expand the accelerated temperature, you get the unroot temperature plus some corrections that depend on this combination R omega. If you do it for the case of a thermal bath with, let's say, a arbitrary temperature T, then you get the same expansion, but with the T. So in fact, it's telling you that the Umbra effect is really causing, these are really still manifestations of the Umbra effect, even though you still have corrections due to the circular motion. And these agree to 3 orders in perturbation theory. And this was beyond what we had expected. And to anticipate the question, does this go further? I don't know. But still, even with the Umbra temperature of your thermal bath, they agree beyond leading order, which was a surprise to us all. So in summary, in this work, we're looking at the thermality and the duality between acceleration and a thermal state beyond the Umbra effect. In general, true, these are distinct phenomena. If you add some circularity, someone with a perfect measurement could distinguish, but no measurements are perfect, so there are still regions within parameter space in which an observer would still be unable to distinguish, especially in these limiting cases. So with that, I'd like to thank you all for listening. I'm gonna have to come over. The echo is. Sorry, could you repeat? The echo is just, I couldn't hear anything.
So when you write this combination of your acceleration,
Circular.
circular motion, single metric.
Yep.
You can calculate the timeline of this metric, and then using Tolman error test law, just the temperature scales as the norm of this timeline.
Okay. Yeah.
Guess it would exactly give the expansion of those corrections that you have shown on your final slide.
Yes. So the question was, if you add the killing vectors together for circular motion and linear acceleration, you have this overall time-like killing vector. And by the Tolman-Ehrenfast law, the norm of this would give the temperature, just so everyone could hear. We didn't actually try that, but because this is not genuinely thermal, so in the case of just linear acceleration, this would I agree, this would give you a over 2 pi, yes, but it'd be interesting to see what it would give for this, because it's still a time-like killing vector. It's a killing vector of Minkowski spacetime because it's just the sum of 2 killing vectors. And if R omega is less than 1, then it's still time-like. No, it'd be interesting to try. Thank you. Yes. It's the sum of boost plus a rotation. So boost in T and Z and a rotation in X, Y. Exactly that.
useless.
Thank you. Sorry, I get to get. Sorry.
Yes. Sorry, devi ancora mettere questo. Come but this, what is, I can press it. Okay, so sorry about this. So the motivation of this project is that, as we've heard in many talks during this week, from Eduardo, from Jose, from Doreen, from Chris, and many other people, we know we are reaching a point in which we can maybe establish a theory of local measurements in quantum field theory. However, the question about measurements stays completely unexplored in quantum gravity. And this is for many reasons. It's very complicated to speak about locality and so on. But maybe we can use the holographic principle to exploit or to transfer what we've learned about local measurements in QFT in the past couple of years to start discussing about measurements in at least semi-classical regimes of gravity. To explain what I mean, I will first review very briefly, because we've seen many times, detector-based measurements and some tools from holography. And then, actually, in the meantime, I will also give some new results. And then I will also, then I use these tools for introducing measurement in conformal field theory and to transfer into the bulk, in the AD anti-de Sitter bulk. So, detector-based measurements were introduced by Jose and Luis Garay and Eduardo. And they are basically they exploit the idea that for Unruh-Devi detectors, which are non-relativistic systems, usually two-level systems, moving in space-time, you can create a coupling which is local, and which leads the interaction between the non-relativistic system and the quantum field. And the interaction Hamiltonian we've seen many times, but it has a switching function in time, which tells where the interaction is localized along the proper time of the detector. Then you have a ladder operator in the interaction picture in the detector, and then you have a local operator of the field, local to the trajectory of the detector. Okay, so everything in this interaction, in these Hamiltonian interactions, is in the interaction picture, which will play a role later. So this allows for introducing a type of prepare and measure scenario in which you start from a separable state. You have the state of the detector, for example, the ground state, and then you have some state of the field, let's say the inertial Minkowski vacuum. Then you switch on and off the interaction Hamiltonian, which creates for you a entangled state. And because the state is entangled, it allows for extraction of information about the field from the detector. And moreover, the insight is that because the detector is not relativistic, you have a well-defined measurement postulate there. So you can apply, for example, projective measurements on the detector, and this will read as a measurement on the field as well. So the detector acts as a probe that when you measure, will give, in this case, for example, two outcomes. The ground state if it's in the ground state, and excited if it's the excited state. And then you also update the state of the field accordingly. In this interaction, basically, I picked that the state update of the field doesn't update if you find the ground state, but you can generalize to more general cases. Now, of course, there is a question of where this update takes place, which is a complicated question. We've heard from Jose as well in his talk in the parallel session. But me and Defco proposed a kind of Helvig-Krauss, very similar to Helvig and Krauss, in which you can use detector-based measurements to induce the update of the state in these two regions. So the detector selects for you the causal past of the measurement, and in the past of the measurement, you say that the state of the field should be the state before the measurement. And everywhere else, so in the causal complement of the causal past of the measurement, you should have the selective update, which basically means that the state update takes place on the light cone in some ways, on the past light cone. Now, this might carry some problems, but everything I'm going to say is consistent with this, and it should be able to, it's easily generalized to other updates rules as far as they are light-like, on light-like surfaces. Now, the problem with this prescription is that it's very algebraic in nature. So you're giving these states, but these states are algebraic. And because usually when you do holography, you need vector states and you need time evolution along some slicings, these are not good for holography. But therefore, what you have to do is to switch from this description to a state description. And what you can do is to come up with some slicing, which is bounded in these two regions. So in the past of the detector, you take a slicing that never exits these light-like surfaces. And in the causal complement, you take another slicing that never intersects the causal past. So this is very different from, so this is in the paper we are preparing. This is very different from Sam's prescription, but it's kind of related. So I prompt you to read his paper on the archive from last week. Okay, if you think about this update, now we have a problem, because everything I told you about the state update was considering the Minkowski vacuum. And of course, when you change the slicing, you don't have access to the state anymore. So the observer describing this red slicing cannot see this Minkowski vacuum. So you have to change your equation of motion for the field such that they are supported on the slices, and you have to redefine your vacuum. But if you compare these two, the two resulting states that you have, of course, in the blue slicing, which is the Minkowski, you can do the usual trick of, like, you solve the equation of motion, you quantize the field. This gives you a set of annihilation and creation operators, and this also gives you a vacuum state, which is defined in this way. But if you do the same thing on the red slicing, you find a very different result. So of course, you can still quantize the field, but you will find a different set of annihilation and creation operators, and therefore a different vacuum. So the picture of before cannot really hold with this new vacuum, unless for some reason these two vacua coincide. Now, it turns out that if you go in the long past regime, so you go in very back in the past of the red and blue slicing, because the red slicing converge to the blue slicing at minus infinity, these two vacua actually coincide at the very beginning of time, or if you have a compact spacetime, it can even happen earlier than that. And now that you have these two states, because we were doing everything in the interaction picture, we never really need to evolve the state. We only have to be careful to evolve the operators that appear in the interaction picture Hamiltonian in such a way that they are consistent with this new slicing. But if we take very short interaction times, this will not turn out to be a problem. So this is everything I need from the detector-based measurements. And now I move on to ADS-CST. Oh, sorry. So I will very briefly give some tools. So ADS-CST is a correspondence that comes from string theory quantum gravity, but you can actually state it in some regimes. You can also state as a correspondence between field theories. So what you do is that you consider anti-de Sitter spacetime. You can picture as a cylinder. Then you define quantum field theory in your spacetime. You look at the asymptotic behavior. This will tell you that instead of considering like all the coordinates in the bulk, let's say, so it's in the inner of the spacetime, you suppress the radial coordinate. So you bound your operators to live on the boundary of the spacetime. And then if you look at 2-point correlation functions, what you get is this result in the yellow box. which is known. So this doesn't come from conformal field theory, but it's known to be the two-point correlation function of a conformal primary of weight delta. Sure. Maybe I can even. No, sorry. So no, it's very strong. Of conformal primary delta, where delta is related to the mass of the scalar field you defined in the Membrere, in the bulk. So basically now you have two theories. You have a theory in the bulk, which is a theory with mass, and then you have a theory in the boundary, which is a conformal field theory. But it's still a little bit unclear how these two theories are related. And this is unclear because quantum field theory in ADS is actually not a well-posed problem. Because ADS is not globally hyperbolic, to give a well-posed problem, you also need to give boundary conditions. Thanks. Boundary conditions means that you also have to give a state on the boundary, which means you have to give a state on the conformal field theory. And once you give the state, you completely restrict the dynamics in the bulk, and which means that physics at the boundary completely controls this physics in the bulk. But how it's controlled, it was an open question for a long time until this paper from 2006, HKLL reconstruction, in which they proposed a procedure for reconstructed bulk field starting from boundary data. Now, the strategy goes that the bulk field you can find the bulk field at this point by integrating against a kernel the boundary field, and the kernel is supported everywhere in the boundary, which is space-like separated from the field. Now, this is problematic for us because we want to consider like services on the boundary, and but luckily this construction was refined, and now it looks more like this. So if you want to reconstruct the boundary, the bulk field, you just have to integrate over a causal diamond in the boundary. So now we have everything we need. I know it was very quick, but we can put a detector on the boundary. The detector is the interaction we take at sharp on time, so we don't have to care about the evolution along the funky slicing in the path of the light and the path of the measurement. And then we do the coupling, we do the measurement, and this will result in two boundary field state. The one in which we did nothing, and the one in which we inserted a field operator. If we go and look at the bulk, once so by the measurement protocol, we create a superposition of bulk configurations. And then once we measure the detector, we select between one between these two possible configurations of field in the boundary, in the bulk. For example, if you measure the excited state, you will create an excitation on the boundary. Now, because this surface divides the yellow and the red region is light-like, you can safely do the HKLL reconstruction or the causal diamond reconstruction. And every time you can consider a point in the bulk, it will be supported to a uniquely defined value of the field in the boundary. So I think I'm running out of time, but as a nice example, we also considered a specific case in which you insert a conformal primary of dimension delta, which is known epsilon's meeting in the Euclidean time, which is a prescription given in this paper for creating well-defined bulk duals. And the bulk dual is a massive particle, as a semi-classical massive particle moving in the bulk along a oscillating trajectory. And what you find is that the mutual information you can extract from the measurement happening at the boundary is related to geometric quantities in the bulk, specifically the mass of the particle and the initial point of the motion of the particle in the bulk. So with this, I thank you for your attention. And here there is a summary slide. Yeah. So I don't know the work. So if you have some references, I would be happy to have. Yeah, yeah. But the difference here may be all the other works that I know, they always do very non-local measurements. So they do projections on the boundary, and so it's not a local measurement theory. But yeah, sure. Yeah, thanks. It's not working anyway. So you mean considering like two detectors on the boundary, and they do measurements? Uh, I mean, okay, so if the detector moves along a superposed trajectory, then it's a little bit complicated because you don't have a well-definite causal path of the measurement. So you have two different causal paths, and it's an interesting question, but I'm not sure what happens then. If you instead mean measuring other observables in the detector, then sure, you can do. Yeah. Yeah, that's a very good question. So everything we've done is in the strong tough coupling. So far it's just a correspondence between two field theories, and the detector is coupled to the field theory, but it doesn't really matter whether it's weakly coupled or strongly coupled. You can do both. It doesn't change much, but it's important to remember that the coupling, the n top parameter, it needs to be very large because otherwise you switch quantum gravity effects, which is of course the next step. So that's what we are going to do. Yeah. Thanks.
Any further questions? It's not. Thank you. We have now Leo Parry speaking about field.
I have questions.
The microphone.
Oh. That's it. Oh, here's the microphone.
How does the
It doesn't work.
oh, it doesn't work?
Yes,
Okay,
yeah,
okay,
Lot of noise.
okay, okay.
And this better is
Yeah, yeah. Okay. Hello. So I'm Leo. I'm a PhD student at the University of Nottingham, and I'd like to talk to you about an ongoing. Huh? It's too loud. This better? This better like this? Okay. So I'd like to talk to you about an ongoing project in collaboration with Adam Wilkinson, my fellow PhD student, and my PhD supervisor, Yoma. So the title of my talk is so field state back action from point-like detectors. So this isn't the back action you may be thinking of. This is not the back action of matter on a metric, but this is really the back action of a quantum probe on the field that it probes. And we heard a little bit about this the other day in Cisco's talk. So, yeah, I'm going to be talking about the point-like Unruh DeWitt detector model. So it's a point-like two-level quantum system coupled linearly to a quantum field phi along a trajectory z. And the difference in energies between the two levels is the gap, which we call E. I think in Waterloo you call it omega, but hey. And so the idea is that this detector will couple with the field and it will make transitions. And then from its transitions, you can learn about the field, essentially. And so this model can be used to talk about the Unruh effect, and we've seen it can be used to talk about entanglement harvesting. So it's a very widely used model. And so just more specifically, so here's the interaction Hamiltonian. There we go. So lambda is a perturbative parameter, so the coupling constant that we take to be small. Mu is the monopole moment operator, which induces the transitions in the detector. So by these ladder operators here. And phi of tau is phi pulled back to the world line z of tau. And chi is this compactly supported switching function, which switches on and off your interaction. And so again, we're interested in the influence of such a detector on the state of a quantum field. Okay, so I know what you're thinking, not another point-like Unruh DeWitt detector, but we've seen them in every single day, so they're very widely used. So one issue with them is that they're singular models in some certain sense. And so the question is, how singular are they when you consider sort of beyond leading order in perturbation theory? And spoilers, they're not very singular. So they're still a good model, even beyond leading order. Okay, so so this is the picture. So consider a detector following a time-like trajectory, z of tau. So we consider this initial uncorrelated product state prepared in the asymptotic past. So rho phi I is the initial state of the field, and rho di is the initial state of the detector. And we consider evolving this state up to some time tf, which is capital T, there's capital T here, capital T of tau f. So given this initial state, the final state is given by this, where u is the unitary time evolution operator. And so assuming that the detector is not measured, then we can get the final state of the field by tracing out over the detector's degrees of freedom. So here, like this, so rho phi f is the final state of the fields. And then we can consider this Dyson series, so expanding the final state of the field in terms of this, so in a power series in the coupling constant lambda. So the leading order, you can see that it's just the initial state, and then there are some higher order corrections here. Okay, so this is the final state of the fields. So then we have a choice. How are we going to characterize the back action of the detector on the field states? So you might want to use the number operator, but one issue with this is that it's not a local observable. And what we'd really like to do is we'd really like to characterize the back action locally in terms of local observables. So two typical examples are the field squared, so phi squared, so expectation value evaluated in the final state of the fields and evaluated at a space-time point x, or equivalently, the stress energy tensor. But so one technicality is that these are quadratic observables in the field, and since the field is an operator value distribution, these expectation values they're formally divergent and they require normalization. So so we consider the point splitting renormalization prescription, where so instead of phi squared evaluated at a single point, you first consider this point split, so essentially the 2-point function phi x prime, with this expectation value evaluated in the final state of the field, and you subtract the same thing except with the evaluated in the initial state of the field, and this gives finite values for Hadamard states. So a Hadamard state omega is one that's 2-point function is locally, so the UV singularity structure is just given by the Minkowski vacuum. And so it can be written like this. The 2-point function in a Hadamard state omega can be written like this. So it has this Minkowski vacuum part, which is singular in the coincidence limit. And it's state independent in the sense that it's universal to all Hadamard states. And then there's this extra piece, say h, which is regular in the coincidence limit, and encodes all the state dependence of omega in this two-point function. And so you can see that if you put this, so if rho phi f and rho phi I are both Hadamard states, you put this in here, you see that this singular part, which is state independent, cancels, and you're left with something that's regular, and also encodes the difference in the state between the initial time and the final time. Okay, so I'll focus on phi squared during this talk, but just note that this is also possible for the stress energy tensor, but I will present some results for the stress energy tensor as well. Okay, so so more specifically, let's consider 3 + 1 Minkowski spacetime, and suppose the initial state of the detector is like so, and the initial state of the field is Hadamard, so this point splitting renormalization method works. And I'm going to also assume that it's a zero mean Gaussian state. So that is to say that all the odd endpoint functions vanish, and all the even endpoint functions can be written in terms of the two-point function. So, for example, the vacuum is a zero mean Gaussian Hadamard state, as is thermal states. And so we'd like to, so again, this is the picture, and we'd like to evaluate this observable phi squared expectation value at a point x, some distance from the world line. So, okay, here's phi squared renormalized. So I've dropped the REN subscript here. So, okay, it's a long formula, but I'd like to draw your attention to two things. So first of all, this integral. So here you see the Whiteman function with the first element pulled back to the world line, and the second element evaluated at the spacetime point x. And this Whiteman function has the I epsilon regulator set equal to 0. And so you might worry that as you integrate up from -infinity to tau minus here, so the proper time at this point, which is null separated from this point, you might worry that this two-point function diverges. But actually, the divergence is exactly cancelled by the 0 in the sign. So actually, as long as chi is sufficiently well behaved at -infinity, this integral converges. And you wouldn't really so it would be reasonable to expect that beyond leading order in perturbation theory, that the point-like unruh DeWitt detector really screams. But so this integral converges, which is a good sign. The second thing is, so in the denominator here we have z of tau minus, so this point, minus x, this point. And you can see that as you take this point closer and closer to the world line, z of tau minus is equal to x in the limit, and so you have a divergence here. But as I said, the point-like detector model is a singular model, so you would expect some divergence like this. But the point is that this is finite everywhere other than on the world line. Okay, so now I'm going to take A to be equal to 1, B to be equal to 0, and I'm going to interpret this state as the ground state of the detector when E is positive, and as the excited state when E is negative. Okay, so one other situation you might expect everything to go wrong for the point-like detector model is in the long interaction time limit. So here's just the same formula as was on the previous slide, just for reference. So how do you implement the long time limit? Well, there's uncountably infinitely many ways to do this, but two typical ways are adiabatic scaling and plateau scaling. So the idea is that you start with a compactly supported switching function, and you introduce a dimensionless scaling parameter lambda, which stretches the support of the switching function such that as lambda goes to infinity, your switching function is on for all times. So for adiabatic scaling, the entire support of the switching function is stretched proportionally to lambda. But in this plateau case, only an intermediate plateau interval is stretched proportionally to lambda. So in this case, it's really just equivalent to setting chi equal to a constant. So for example, set chi to 1. And again, have a look at this integral. This integral converges as long as this Whiteman function here has sufficiently strong decay at minus infinity, which is the case for the vacuum and a thermal state. So even in the long interaction time limit, if the initial state of the field is a vacuum or a thermal state, then this integral still converges, and it's still finite everywhere other than on the world line. And then you can contrast that with the detector's transition probability, which actually diverges in this limit. Okay, so how long do I have? 3 minutes. Okay, let me see. Okay, let me show an example then. So, for example, consider a static detector in the vacuum. So the simplest case possible. So here is the space-time diagram of the world line, and R is so in spherical coordinates, R is the radial coordinates. And if you consider the long time interaction limit, this is what phi squared looks like, phi squared renormalized. So here we have the heavy side theta function. There's a sine integral, cosine integral. And the interesting thing is that this is non-zero even if the detector is prepared in its ground state. So a static detector still has influence on the field state even if it's prepared in its ground state. So you can see that here, so even if E is positive, there is some, so phi squared is non-zero. And this is in contrast to the detector's transition rate, which is only non-zero if the detector is prepared in the excited states. Okay, let me skip this actually. But so you can do a similar thing for the energy density of the field. So here's the energy density in the long interaction time limit. And as you can see, so it's doesn't just have a theta of minus E. There's also some, it's also non-zero for E positive. But if you look at the radial energy flux, then this does just have a theta of minus E. And so it's really only non-zero if the detector is prepared in the excited state. So in the long interaction time limit, a static detector only radiates if it's prepared in the excited state. And then, okay, I also wanted to show you something else, but I think I'm running out of time. Essentially, let me go back. So in a similar sense to Cameron's talk a few talks ago, he was interested in how similar is acceleration and a thermal bath. So you can ask a similar question here. So is this duality between acceleration and temperature also seen in the back action of the detector on the field? So consider a static motion in a thermal bath with inverse temperature beta in spherical coordinates, and a uniform linear acceleration in the vacuum with proper acceleration a in Rindler coordinates. So instead of t, x, y, and z, we have capital R, capital T, rho, and psi. And I'm going to consider the case where rho is equal to 0. So we're looking in the tz plane of motion. The world line is located at r equals 0. And this splits the wedge into the right of the wedge and the left of the wedge. So the right is given by r greater than 0. The left is given by r less than 0. And you can ask, is phi squared the same in these two cases? And the answer is no. Actually, they're quite different. They're significantly different. So if you set t equal to capital T, r equal to absolute value of capital R, and then you relate the inverse temperature and the acceleration by the unroot temperature, what you find is that actually they're related by this multiplicative function, which is just a function of A and R. And so here is a plot of this function, this multiplicative function. So to the right of the world line, the static thermal case is much, much larger than the Rindler vacuum case. And to the left of the world line, in this corner of the wedge, the Rindler vacuum case is much larger than the static thermal case. And they're only equal on the world line. So they both blow up on the world line, but they blow up in exactly the same way. Okay, so this is just another example. But so the goal was to investigate the influence of a point light detector on the field. And to do so in terms of local quadratic observables. And it turns out that these are finite everywhere other than on the world line, even in the long interaction time limit. Okay, and then I showed you some select results. And then, future work could involve, so what is the effect of having a spatial smearing in your detector? Or maybe, considering a more general quantum field detector. What is the effect of measuring the detector on, say, the stress energy tensor? And doing similar calculations in curved spacetime. Okay, and so thank you for listening. Yeah. So B shows up in. So B is responsible for so if you look at, for example, phi expectation value, you'll find B. And so presumably if you look at phi cubed expectation value, you'll see B. But for even powers of phi, you'll only see A. So this B is responsible for giving your field, for giving your state a mean, non-zero mean. Okay, so well, I mean, you could look at the expectation value of phi. Yeah, you could. We didn't do that, but you could do that. Yeah, yeah, absolutely. Yeah, yeah. But I suppose the point is here that phi squared. We're hoping for phi squared to behave as like a proxy for, let's say, the energy density or something. Yeah, yeah. Ah, uh, that's also Hadamard and zero mean Gaussian. Yeah, I'm not sure. I'm not sure. I mean, if you pick a state out of the hat, then I think it would. This would blow up. Yeah. Oh, sorry. Yeah, I mean, so the last thing I know, I went through it very quickly, but so this is a uniform linear acceleration in the vacuum on inertial. So yeah, in Nottingham we're interested in circular motion, so it would be very interesting to look at circular motion. But yeah, so that's definitely in the pipeline. Oh yeah, yeah, yeah.
About our information across the horizon.
Thank you. So before I begin, I would like to thank all of the organizers and participants for making this conference a truly wonderful event. My name is Sijia Wang. I'm a student from the University of Waterloo, and today I will talk about some work that I've done in collaboration with Maria Rosa Preciado Rivas and Dr. Robert Mann, also from the University of Waterloo. And the research is titled Harvesting Information Across the Horizon. So, as we know, there does not exist a full theory of quantum gravity. However, relativistic quantum information can provide us with tools to investigate the overlap between the two disparate theories of GR and QFT. The overarching purpose of this work is to better our understanding of how gravitational fields can influence the correlation properties of the quantum vacuum. In some situations, we may be interested in taking an operational approach using particle detectors. That is, a particle is what a detector detects. The simplest model is the en route detector, which is a two-level system that has some energy gap, which I label with capital E. And as this detector moves along some trajectory, we may compute its response. And this helps us probe characteristics of the quantum field that lives in a certain space-time configuration. One situation in which we would suspect that the interplay between GR and QFT would become significant is when there's a black hole. So in black hole spacetimes, we could look at, for example, detectors that fall behind the horizon and compute their transition rates. Or we could look at the correlation that could be harvested by two or more detectors in the vicinity of a black. The interest of our work is to combine these two types of problems. So we want to look at correlations that are harvested by two detectors, but also have those detectors fall behind the horizon and dynamically. So we look at the problem dynamically, and maybe something of interest would be like what happens if one detector interacts only inside of the horizon, the other interacts only outside, what kind of correlations do they see? Now I described the setup of our simulations. So we have two en route detectors that are initially at rest at some at the same position outside of a static 2 + 1 dimensional BTZ black hole. The detectors are coupled to a massive quantum scalar field in vacuum state. Then we allow the detectors to fall radially into the black hole, and we compute the mutual information between the detectors along the trajectory. So detector B at the bottom switches on first, and then detector A switches on, and we select the separation between the switching functions such that they are greater than their width, so there's no overlap. And for this one simulation, we generate one value of mutual information, which we plot at the proper time that we take to be the time at which detector A switches off. Then we reset the detectors to their initial positions and states. We shift the switching functions further to the right, that is further along the trajectory. And we allow the detectors to fall. This lets us generate the next point and our mutual information. Again, just one more time, to drill it in. So we reset the detectors to their initial states. We shift the switching functions, and we let the detectors fall. And we do this many times to generate a function of mutual information versus detector proper time. And now we selected the 2 + 1 dimensional BTZ black hole because it is easier for us to compute these quantities. But at the same time, we expect that this would provide insight into the problem in higher dimensions. So here I present just the same thing, but mathematically. So here we have the line element for the static BTZ black hole. It has a horizon where f of r ranges, and the space-time has negative cosmological constants. We consider a quantum scalar field which satisfies the Maxwell-Stein-Gordon equation with conformal coupling, and we compute the Whiteman function, which is given by this expression here. And the Whiteman function can be computed as the image sum running from n equals -infinity to +infinity of these terms that involve 1/square root type quantities of the geodesic separation, sigma, which sigma can be calculated for the coordinates from this bottom expression, and the quantity zeta here in the Wang function is a boundary condition of the field at infinity. So the interaction Hamiltonian that we assume, we couple the monochrome moment of the detector to the quantum field. We assume that the coupling constant lambda is small, that it admits a perturbative approach, and that the energy gap of the detectors is the same. And if the detectors are initially in ground state and uncorrelated, and with this interaction Hamiltonian, we can calculate the final density matrix of the detectors, rho AB, to lowest non-vanishing perturbative order, relatively straightforwardly. And to get the mutual information, then we require the PA and PC, which are the PA and PB, which are the transition probabilities of detectors A and B respectively, and also C, which I will call the correlation term. These come from rho AB at lowest order. So here written now mathematically is the trajectories and the switching functions. But this is exactly as I showed in the animation a few slides ago. And for this trajectory and switching function, then we get these concrete forms for the transition probability and correlation, and these are computed numerically along the trajectory. So the gist of our results is we find that mutual information goes from monotonically decreasing to decreasing and then increasing, and finally to monotonically increasing as the mass of the black hole decreases, or the width of the switching functions decrease, or the width of the switching functions and the temporal separation between them increase proportionally. In the following slides, I will show the results for the case of varying black hole mass, but the other two cases follow analogously. So here's what we get when we vary the mass of a black hole. So we plot the mutual information versus proper time, and on the right-hand edge of the plots at pi/2 is when the detectors would reach the singularity of the black hole. So we see, again, that as when the mass of the black hole is relatively large, we have this monotonically decreasing mutual information. And then as we lower the mass of the black hole, then we see this inflection point start to develop and grow leftward. And we know as well that when the detectors are far away from the horizon, then the mutual information is nearly constant. So this is like in ADS3, but when the detectors get close to the horizon, then the presence of the black hole becomes known. And so we have that the mutual information deviates from its constant value. So digging a little deeper, if we look at the components that go into mutual information, we find that so here in green is the transition probability, and in yellow is the correlation C, and in red is the overall mutual information. So we observe that when the mass is large, then P grows faster than C, but as the mass decreases, C starts outpacing P, and this is causing mutual information to grow. So if we interpret P as a noise that competes against the correlation, then we could say that smaller mass black holes are statistically quieter. maybe we want to understand, what's driving the growth of the correlation. So let's consider again the Whiteman function. And this quantity under the first square root can vanish when the 2 points are null separated. And if we want to calculate, for example, the transition probability of one of the detectors, then we would have this integral, which involves the Whiteman function inside an integrand. Now, even if the Whiteman function goes, or even if this quantity under the square root goes to 0, we can still get a value for the transition probability. But when these singular points in the Whiteman function coincide with the limits of integration, then we have mathematically interesting points that are known as glitches. So to kind of illustrate what's going on, suppose we want to compute the transition probability of a detector, and this is the white line is the trajectory of the detector, the red segment is when the detector is switched on. These glitches occur when the boundaries of the segment are separated by a null array. Now in ADS3, we don't get that because we know they are timeline separated. However, in BTZ, because there's a phi identification, these null arrays can wrap around in the phi direction, and so we get one glitch for every term in the image sum except for n equals 0. And just as an aside, this glitch, the term glitch was coined in the previous research that was also looking at detectors in BTZ space-time. So here is just a small subset of the glitches that we see, but I think it's illustrative. And again, we're varying the mass of the black hole. So we see that the P glitches, which are the solid dots that are connected by lines, and the C glitches are the hollow dots. So as the mass of the black hole decreases, the C glitches grow leftward faster than the P glitches. Why is this significant? Well, this is significant because recall in the previous slide, or a few slides ago, that when the detectors are far away from the black hole, then the mutual information is constant, and P and C are also constant. And we just said that the glitches appear because of the phi identification. So the glitches are sort of like an indicator of when the BTZ effects become prominent. And so if the C glitches occur much earlier, then we are going to see that the correlation will start growing and outpacing the transition probabilities, leading to the inflection points in the mutual information. So in conclusion, this is kind of an interesting simulation. We looked at a range of the parameter space to see what these detectors see. We find that mutual information is non-vanishing and non-monotonic along the entire trajectory, and that even relatively simple black holes, like the 2 + 1 BTZ with constant curvature, have non-trivial impacts on the correlation properties of the quantum vacuum, which we can map out with detectors. So I thank you very much for your time and attention. Yes.
I want to design like a slow slide.
Yeah, so that's not quite the situation that we considered. So the situation that we considered is that the two detectors are at the same location, but their switching functions are separated, so they're never on at the same time. So that's how we simulate sort of the separation. But yeah, that would be another approach, like what you suggested, where one detector is lagging behind the other.
Okay, thank you.
Yeah.
So how do you simulate the small the measure that is all given so
Yeah, so we look at everything in terms of the proper times of the detectors.
okay, so you're limiting the confidence.
Well, it's not going to go to infinity, so the proper times will go to pi L over 2, where L is like the ADS length.
There are no further questions. So we can have a speaker again. Is Luis Barbado. Who will speak about boundary
Does it work? Okay. Perfect. Think it's where's the drive? Okay, there we go. Yeah. Okay. Can you hear me? No? It's with a okay. 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 Thanks, the organizers, for giving me the opportunity to present this work, and thank everybody for staying till the very end of this very nice conference. I'm going to present a work that I did in collaboration with Laura Nielman from the Universität Hannover. And it's about the excitation of particle detectors and superposition of trajectories in the Sitter space-time. There have been other works in this topic. Already. Shall I take it? Okay, better. There have been other works in this topic presented already by Wang, for example. But the sort of approach we do is different. The model of the detector is slightly different. And although it may seem that it's just a nuance, we will see that the sort of phenomenology that we want to find requires these different sort of detectors, a multi-level energy detector, and therefore we explore different, as I said, different phenomenologies than other approaches on the topic. So, of course, the intention of this work is to try to bring together concepts of quantum field theory in cavity space and notions of quantum reference frames. And operational way of doing so is to use particle detectors, and instead of following well-defined classical trajectories, we'll follow quantum superposition of trajectories and see how they perceive the field and how they get excited with the field. The field theory that we introduce is the easiest one. It's a massless scalar field in 1 + 1 dimensions in some deciduous space-time. We choose a Euclidean or Bunch-Davis, also called, state for the field, in which free-falling observers would perceive a thermal spectrum with temperature proportional to the acceleration rate. And we consider families of observers, which define what are called static patches. This is a compactification of the space, and this would be one of the static patches, where families of observers that keep their proper distance with respect to one another constant, right? And in in the basis of modes natural to these observers, this vacuum would look like this, which is basically once one traces for the unseen part of the part that is inaccessible for these observers of the space, then you get a thermal spectrum, right? And with temperature proportional to the inversely proportional to the proportional to the expansion rate. So Of course, this does not mean that all observers following the static trajectories with respect to keeping their distance with respect to one another will see the same temperature, because only one of them can be a free-falling observer. The others will have to accelerate towards him to keep the distance, so they will increase the temperature they see, which can be ascribed to an Unruh effect that adds up to the perception of the thermal radiation by by the cosmological particle creation of the expanding universe. So the model of detector, as I said, is different from just Unruh detector. It's point-like in this sense; it coincides with a usual Unruh detector, but it's multi-level, right? It can have 2 or more excited levels, right? And this will be crucial for the sort of phenomenology that we are going to find. And as I said, instead of following one well-defined static trajectory, it will follow a semi-classical quantum superposition with different amplitudes. I put here the initial state on one given static patch, right? We introduce an interaction term with the field, which the detector will interact with the field and point-like, but of course the position of the detector will be an operator, which will evaluate different along each trajectory. And another difference with respect to other works on the quantum superposition of trajectories of detectors in the CETER is that we use a switching function. We are going to consider the regime with a very smooth switching function that lasts for in the limit where it lasts a very long time with a very weak coupling. The advantage of this is that we are going to be sure that all the results I'm going to show we have no contributions whatsoever from the switching process, right? In that limit, all what remains only depends on the trajectories, on the energies of the detector, on the on the characteristic of the field, but not on the switching mechanism. And then, well, I introduce here the main result, which is how after this process of letting the detector, putting it in a quantum superposition of trajectories, static trajectories with respect to one another, and letting it interact with the field a long time and switching it off, how it gets excited. And of course, in order to find some non-trivial result, we need to measure first the detector trajectory in a non-trivial basis, right? If we measure it to be just in one of the trajectories, then all coherencies are lost. If we do so, we trace out the field, we measure the detector to be in some, we do some interferometry, and we measure it to be in some non-trivial superposition of trajectories. Then this is the state for the internal degrees of freedom of the detector, so for the excitations. I will comment. I will describe the state in detail. Of course, first we get a contribution of the detector not having get excited. This is the highest one, but this is a 0 order. And then to first order in the coupling, this is a coupling intensity. We get its first order because this is a coupling time, and we set the coupling time to be inversely proportional to the coupling intensity. So this would be overall first order in the coupling intensity. We get first contribution which is diagonal in the internal energy levels of the detector, and this is just a complete mixture of the different temperatures that would be perceived along the different trajectories that the detector has followed. So if we had only found this would be a trivial result. There would be nothing new. All coherencies of the quantum superposition of the detector got lost through the interaction with the field, and there's nothing. They just complete mixture. But this is not the case. We also find some contributions here. Of course, we find with a thermal spectrum. This is I don't want to go into the details of the notation, but this is basically a thermal spectrum. We got another contribution which is of diagonal terms, so coherencies of the internal energies of the detector. Of course, this is if it was just only one level of citation, this this would not exist, of course. So this is a non-trivial result that you can only find if you have more than one excitation level. And this is a novel term, and I will try to argue the to discuss it physically, right? First, these sort of terms, these off-diagonal terms, only appear in the case that the quotient between one of the energies and one of the Tolman factors of the one of the trajectories followed, and the other energy of the off-diagonal term with its quotient with a Tolman factor of another trajectory, they are equal, right? Of course, the static trajectories, they have different accelerations. They have Tolman factors with respect to one another. And what's the physical interpretation of this? Well, if one thinks that, yeah, thanks. If one thinks that the excitation of the detector is produced by absorbing a particle of the thermal bath of the field, then this condition is basically that the possible absorption of this particle through one of the trajectories or through the other should have the same energy. This absorbed particle should be the generating energy. And this is reasonable because if the excitation along one of the trajectories or the other would be not the same in energy, this would mean that the state left of the field through the absorption of the particle would be different along one trajectory or the other, would be distinguishable. So therefore, after tracing for the field, no coherencies could be left, right? There are coherencies left because the particle absorbed through one trajectory or through the other happens to have the same energy, right? And the other thing is that these off-diagonal terms are weighted by this thing, which is basically a scalar product. I cannot go into the details, and that this weight takes this form depending on the position of each of the two trajectories that contribute with this term to the excitation, right? This would be the position of one of the trajectories and the other. And this is for different energies. These are higher energies and lower energies, right? And this, so the behavior of this scalar product is basically telling you that the more distant the trajectories are, the smaller, with some fluctuations, but basically the more distant the trajectories are, the smaller the off-diagonal contributions are. And this also has a very natural physical interpretation. And it's, again, if there's a particle absorbed by the field, and in order to have coherencies, you don't want that the state left of the field through one trajectory or the other can be distinguished. They need to have some overlap. It means that the trajectories need to be close because the particles are absorbed around the trajectories. So the trajectories are close. The particle absorbed through this trajectory or through this other trajectory, the state left on the field after the absorption are not fully distinguishable, and therefore, after tracing the field, some coherencies are left. If the trajectories are very far away with respect to one another, the state left for the field with an absorption through one or other trajectories would be fully distinguishable, and therefore no coherencies can be left. So somehow this result, the non-triviality of the result of this result, is telling us that this is giving us a sort of a shape of the absorbed particle, a spatial profile in the static coordinates of the absorbed particles around the trajectories, right? These are the main results. There are some physical discussions in the full article, and this article is part of a series of works in which we studied different phenomenology of quantum field theory in Capel space through a very similar procedure. There was first a work by on the Unruh effect and on Hawking radiation perception, another one, and future works would be to see whether the other approach to the phenomenology of quantum field theory in Capel space, which would be through Bogoliubov transformations, whether one can also figure out how to generalize that to using quantum reference frame notions. And of course, and this has been done for other works on quantum superposition of detectors in de Sitter space, how to relate, how to make a comparison between this situation in which the trajectories are in a superposition and the situation where it is the metric that is in a semi-classical superposition. This has been done with other approaches, and eventually we would like to do that also with our approach. And this is it. Thanks for the attention. You're welcome. No, this part is basically an idea for future work, because so far the only, like, so to say, self-consistent way of trying to bring together notions of quantum reference frame to the phenomenology of quantum field theory has been through particle detector, that at least through this approach. But eventually, this is just a suggestion for future work. On a first stage, I wouldn't have any more concrete idea on how to build up this notion in the formalism of Bogoliubov transformations.
You can describe the superposition interface. How does that just the face minus 6 plus on the superposition interface?
The phases in the quantum superposition. Yes, they are included. I didn't want to comment that because but all these are the amplitudes and they can have phases. I mean, eventually you can superpose these with any phase. I guess you could. I think if you have the correct, like, different energy levels and you introduce here the correct phases, you could eventually cancel or not cancel these terms and accordingly. Yes, I guess you could, because here you have the different amplitudes and the phases. They don't contribute here, of course, but to the diagonal terms, but they do contribute to the off-diagonal terms. So you could do some interferometry where depending on what you measure with which phases, you could cancel the contributions or not. Yes.
No further questions, thanks.
Yes, you can connect to your own laptop.
All right. Good afternoon, everybody. Thanks for staying to the very end, and thanks to the organizers for putting this wonderful conference together. I regret that I could only attend the very end of it. So my name is Daniel Braun, and this is work together with Llorenç Escola Farras. Actually did his master thesis in my group on this topic. So before I go to causal inference in quantum mechanics, let's recall what causal inference in classical mechanics and classical statistical analysis means. So actually I have a hard time seeing this from here. Okay. So the causal inference is described, for example, in this book by Judea Pearl, the Book of Why.
saying, first of all, it's something between random variables. So the first random variable x and another one y, and he says a causal inference from x, another random variable y, is if y listens to x. And what he really means, and writes later, is that y is a function of f of x plus some other random variable z. Now, in order to analyze this, the gold standard of causal analysis is the randomized controlled trial. This was apparently done for the first time in psychology, even at the end of the 19th century, and then moved into agriculture by Nyman and the famous Ronald Fisher. And since the 1940s has been used in the clinical studies. That's where most of people have thought about this. So how does it work? Suppose you observe some correlation, for example, between taking aspirin and losing a headache. Then you might wonder, is this just a correlation, or is there maybe a common cause, right? So what you do is, well, you have to cut this possible link. So this link up here, you want to cut, and the way you do it, you say, do aspirin. You choose people, you tell them you take aspirin, you take others, you tell them don't take the aspirin, and hope they do that actually. And so you remove this possible inference from the common causal, from the common cause. And so if there's still any relationship between these two random variables, then you can say, okay, there is some causal inference directly from this random variable to that one. So meaning the causal inference is there if and only if the probability for getting no headache or losing the headache by do aspirin is different from this probability for do not aspirin. And I want to emphasize here this do. What we're looking here is not just an observational scheme. So these conditional probabilities that you all know about are different from these do probabilities. So there's a whole calculus that was developed by Pearl, the so-called do calculus, do probabilities, a mathematical framework that allows to really automate nowadays causal inference. You need a dialectic acyclic graph and so on, but it's a well-developed formalism, and it really goes beyond correlations. And so how to transfer this to quantum mechanics? So, well, in quantum mechanics, let's also look at this tripartite setting. So we have Alice here, we have Bob there, and instead of random variables, they have states, rho A, rho B, and there can be a common cause, but it can also be more general. It could be an environment. It could be the medium that actually propagates the causal influence. And okay, so these states live in the Hilbert space, and you can think of them as reduced states of a larger common joint state. And so the same question arises here. Does rho B listen to rho A? And it really means we have to look at rho A and see if rho B changes. So if you do rho A, you set rho A to a certain value, to a certain state, does rho B change? And that's the whole philosophy of what I'm going to talk about in the following. Maybe one technical thing will assume that A and B are finite dimensional Hilbert space, but the environment can have infinite dimensional Hilbert space. And so we look at quantum channels on A and B, and well, in the usual sense, rho AB is mapped to rho prime AB, and this is done by having here these Krauss operators on the whole system, and then trace out C, so it will give you a channel just between AB and A prime, B prime. And you can convince yourself that you should actually start with initial state that factorizes out C. If you don't do that, you actually don't have just rho prime AB as function of rho AB alone, but also rho C will come in. But if you factorize it, then you can absorb rho C together with the Krauss operators in a description of your channel. You can also convince yourself quite quickly that you should factorize the initial state between Alice and Bob. Or classically, you would do that because you don't want to start with correlations. You want to see if correlations are created. But quantum mechanically, it's even more important because you could have just a measurement on one side, and the state would collapse, and so the state changes. But we know that such a measurement and a state collapse should not transmit any information, and so we want to exclude that. So the way to do is we factor also rho A and rho B. Now in the following, I will introduce or actually use this kind of propagator, which is written down here, which is obtained by writing everything in coordinates. So we always have 3 coordinates for Alice, Bob, and C, like Charlie. And so this is just writing out the equation up here in the coordinates. We trace out C, so it's this the sum over M prime here. We also trace out Bob, and so in the end it's It's really a propagator from AB to A prime. Okay, and that's the technical object I'm going to use. And so here's our definition of causal influence in quantum mechanics. We say that B does not causally influence A for a given initial state rho A, if and only if rho prime A, defined this way, trace out B, is independent of rho B. Okay, and if that holds for any rho B, then we say that B does not causally influence A. And we denote it with this right arrow with a slash. If not, then we say B causally influences A. So B right arrow A. Okay, that's our definition. And once we have this definition, we can prove a simple theorem. It's just really based on linear algebra, so I will not prove it, but it just tells you what the structure of this propagator has to be in order not to have any influence from B to A. And essentially, if you look at it, means, well, it has to be diagonal in this indices K and L, but also independent actually of this indices K. Okay, there is no sum convention in this expression here. And then you can look at all combinations, and typically for a general unitary of the full system A, B, and C, typically you find influence, causal influence from A to B, from B to A, but there are also cases where you don't have any influence from A to B or from B to A, and all four combinations do exist. There's also something you can prove quite easily, or see even, there's not much to prove actually. There is no transitivity. So if A causally influences B and B causally influences C, does not mean that A causally influences C. If you don't believe it, it's very easy to show and can tell you afterwards. But we don't just want to know if there's a causal influence from A to B or the other way around. We also want to know how much causal influence is there. So we want to define a measure of causal influence. And the way we do it, we start from initial state of Alice, which is just unitarily transforming given fixed state 0, and then we just average over all the possible initial states defined this way. So we choose V from the unitary group and just average with the Haar measure of the unitary group, and then we look at this derivative of her final state with respect to the initial state of Bob. Okay, and take the absolute value square of this and sum everything up. So these are complex derivatives. In general, these matrix elements are complex. So I have complex derivatives of a complex number with respect to another one. But these are well defined because of the linearity in the propagation. And for the same reason, actually, the whole expression is then independent of rho B. Once you derive and differentiate the linear function with respect to rho B, it drops out. And in fact, we can do this integral exactly. So analytically, we have to do this invariant integration of the unitary group. And then you find this explicit expression for this measure, just expressed in matrix elements of that propagator. And you see it's a rather simple expression. And there come in some other matrix elements, which, however, are just the numbers, Kronecker deltas and phases and so on. So once you give me a propagator of a joint system A, B, and C, I can tell you what is the causal influence between them. And here are some properties of this measure. So first of all, I is equal to 0 if and only if there's no causal influence, according to the first definition I gave you. This is certainly a property that we want to have. Then secondly, the measure is invariant under local unitary pre-processing of Alice and local unitary post-processing of both Alice and Bob. So the first property is kind of clear because we averaged over all unitaries on Alice side. So any further unitary transformation, we're going to change anything here. And the second part here is definitely makes sense and is something you want to have, because once the causal influence has happened, it should not depend anymore of what they do locally afterwards. And then you might say, okay, what is the scale for the whole thing? It's not a measure that's just between 0 and 1, but the scale is set again by a Haar average. So if you take unitaries of the full system A, B, and C and average this, the causal measure of causal influence, then you get this expression here, which is just a number depending on dimensions of the subsystems. And so that sets the scale for the whole thing. And you might look at different limites. So for example, if the final system, the environment becomes very large, then you see it's asymmetric in B and A. So the larger the B system, the larger the possible causal influence. And for A, it's the other way around. So a large system on Bob's side can have more influence on Alice side, and if your system is small, then also the influence go up. So here's an application to some simple examples, just basic quantum gates. So if you think about the CNOT operation, you have a control, you have a target, and you would intuitively think, okay, the causal influence is from the control to the target. And that is true, but there's also an inverse effect from the target to the control. And here is how much. So C0 is 0.66 in one direction and 1.33 in the opposite direction. And there's actually a physical mechanism behind this, which is quite well known in quantum information theory. It's, for example, the phase kickback from the target to the control. That makes also that the controlled state depends on what you do on the controlled, on the target side. Okay, and yeah, I will not go through the details of the other examples here. I want to come to a final example here, which I think is very interesting. And this is, I think, 2 spins, 1/2 sitting in an environment, a thermal environment. So it's 2 spins, 1/2 boson model. So here it is, this Hamiltonian, SA and SB might be just some Pauli matrices. I don't even specify which ones, but just say that they have eigenvalues A and B, AI and BK. Here is the path of harmonic oscillators, and here's the coupling. So there's no rotating wave approximation, but the trick to solve is that you send omega to 0. Then you can exactly solve it. Very simple. It becomes just a dephasing model, and something I did a long time ago before. And so you can just calculate what is the final state as function of the initial one. You get these differences between eigenvalues, and then this function f of t, which is linked to the real part of the bath correlation function. And here also the phase phi of t that comes in here, which is linked to the imaginary part of the bath correlation function. Both are functions that are even in time, and so you plug this into the formula they gave you for the causal influence, and you find this result here. And so as long as A0 is different from A1 and B0 is different from B1, then you get a causal influence, and it decays exponentially with this function f of t here. And one remark here, so as I said, I mean, these functions are time reversal invariant. So if you're looking for breaking of, let's say, having only 4, and the breaking of the symmetry in time, so have only forward causal influence, it will definitely not come from this type of model. You have to look for such reasons outside of quantum mechanics. Now here's a specific example with numbers put in. So suppose these 2 spin 1/2 systems are on double quantum dots coupled to black body radiation, here taken at the temperature of the cosmic microwave background. And you start in initial product state ++, and then you find this kind of plot for the causal influence as function of distance between them and the time that has gone since you coupled them to the heat bath. And what you see here is that the causal influence happens much, much later, much after the light cone. So the light cone will be something down here, x equals ct, and this line here corresponds roughly to t larger or equal than 10 to 11 x divided by c. There's a time scale in there, which is the thermal time defined down here, which is rather small in this example. Now, if you look at this plot, it's actually very reminiscent of the plot of reservoir-induced entanglement that I proposed, and Eduardo knows quite well about it because we discussed it many times, like 23 years ago. The plot actually looks almost identical. And seeing this, well, then I said, okay, maybe we just have to adjust the prefactor. If you do this, you fit the prefactor and take then this difference to be minimal. And then you see that the difference between the causal effects and the reservoir-induced entanglement is very small. It's only up to plus or minus 5%. Nevertheless, they are not identical. And in fact, the entanglement will at some point, if f of t is large enough, will just go exactly to 0. So it only works up to some finite time before the dephasing becomes strong enough. And then the entanglement will be gone, whereas the causal influence continues, as we have seen in the previous example or previous formula here, even if f of t goes to infinity. So not the same, but they're intimately linked, it appears, and in particular this structure that you get both of them only rather late, not right after the light cone, but really orders of magnitude later is common to both. And with this, I come to the end. Here's a summary. So we defined causal influence in quantum mechanics in a rather straightforward, I would say, pedestrian way, but that really reflects what has been done in classical causal analysis. And we have a tripartite setting, as is also usual in classical analysis. We have a formula or a measure defined that we can apply to any quantum channel. You just need a propagator. So it is computed already. There's no maximization also in there. And there seems to be a deep connection to this reservoir-induced entanglement. Here is the publication. There are many more results in there. A causal switch, for example. Ask me if you want to know about it. And that's it. Thank you. Yes. Well, you still do something on Bob's side, right? You conjugate your CNOT with two Hadamars. So you do a different thing on Bob's side first. And on Bob's side, there's no invariance on the first transformation. So it's a really different situation. No, I don't think so, because it's part of the do action, right? Bob can do something, and what he does influences what Alice will have. So, I mean, this fact of setting a certain state on Bob's side is important. Well, yes, I mean, it does. I mean, you start from some certain state, and then it does a Hadamard, or it does not. So it will give you a different state. And the measure in the end is averaged over all that happens on Alice's side, all her initial state. So you can make a total unitary transformation if you wish, and that influences the channel.
Of this very interesting conference. Thank you.
Now that it's been announced, so maybe you know very special stuff. I start doing the meetings, you're gonna get copy, find the bus, then it's just going away. The time is the seven minutes, so very fast.
Yeah. 4:45. Yeah. Just one very last thing. Sorry, well, that was long. One very last thing. So this is officially the last talk of the RQI North. I would really like to thank especially Alessio for all of the work, all of the running around or organizing this conference, because really it's a thank you so much for doing this. Thank you so much. And please come to the General Assembly because typically these acknowledgements and everything happen there. And then we also make some important announcements and important decisions, such as next RQI North meetings and all that. So thanks, Edu, for announcing that. Thank you.
We want to take it in my section. Conference with no names. Session.
It's in that room over there, A4.